So we're going to be speaking about privacy in machine learning for those who have just joined.
Yeah, perhaps I can make a brief intro. What we're going to be talking today is about the idea of differential privacy and how we can use it to train machine learning models with privacy considerations in mind. So yeah, we're going to be talking a bit about some techniques that we can use to employ these ideas. So yeah, perhaps we wait just 1 or 2 more minutes and we'll start.
Okay. Hello, Wolfram. So as a reminder for everyone, you can send questions in the Q&A section of Zoom or the chat, and we will take on those. We're going to have the presentation, and then at the end, we're going to have a Q&A session, and maybe even if you have relevant questions during the presentations, you can send them through the Q&A, and we'll let Seba know that he has some stuff to answer. Okay, so don't be shy, please.
Yeah, for sure. If you see that I'm not seeing the Q&A, please let me know via audio. So that I can answer all your questions.
I will do that. All right, 1 more minute and then we get started, okay?
Sure.
So Seba, what got you into privacy preserving machine learning?
Well, to be honest, I've been doing a bit of work for my research thesis on this project. We had a particular problem. It was a very typical problem for this kind of techniques, which is that we had some sensible business data. We wanted to make predictions on new data, but this data could really not be released at all. It was from a government agency, so there was some legislations to take into consideration that the privacy of that data was really important. So we started researching on techniques that we could mathematically prove that this training data won't be compromised. So yeah, that's how I started, and this is one of the techniques that we've been using for this problem.
Nice. Okay, so I think that we should get started now.
Okay.
Let me see here. Okay, so thank you all for joining. As we were saying before, and if you have just joined, we're going to talk about privacy preserving machine learning. That is these new techniques that are coming up to be able to train and test models without having access to the raw data. And in a world of privacy regulations and sensitive data that people don't want to lose control of, this is increasingly important. So a little bit of intro about Tryolabs in case that you don't know about us. So we are basically a machine learning consultancy or solutions company. That means that we work with other companies and help them create business value by partnering with them or helping them throughout the phases of machine learning development. So this is from the initial discussions on what problems to tackle, the prototyping, these ideas to R&D development, and then putting these systems into production and making them scale. So we have worked with quite a large variety of industries, and we have like 3 main areas of expertise. One is natural language processing, that is understanding text at scale, computer vision, in which we understand videos and images, predictive analytics, and we have been doing a lot of work lately here in topics such as demand forecasting and pricing. We were founded in 2009, so we've been in business for a little bit over a decade, and we are now close to 55 people with offices in Uruguay, South America, San Francisco, and Luxembourg in Europe, where we just recently opened. And hello, Pablo, our person in Luxembourg. So again, remember that we are going to have a Q&A session, and you can send questions in the chat or in the Q&A with the Q&A option of Zoom. So without further ado, I give the intro to Seba to introduce himself and what we're going to be speaking about today.
Okay, cool. Well, thank you very much, Alan. A bit about myself. Well, I'm Sebastian. I work in software engineering here in our offices in Uruguay, Montevideo. So yeah, let's see a bit about the agenda for today. First off, I'd like to introduce this problem by showing some common privacy vulnerabilities that the machine learning models can have, and how we can sometimes accidentally expose the training data without realizing that. After that, we're going to be presenting the notion of what differential privacy is, the privacy guarantees that this framework allows us to have. So we're going to be progressively building some intuitions around it to arrive to the formal definition of it. And afterwards, we're going to be talking about a technique that's called a PATE. It's not the food, but it's actually an acronym. It stands for Private Aggregation of Teacher Ensembles. So it's a technique that allows us to train machine learning models with these privacy guarantees in mind. Okay, so first off, let's start looking at some examples of the privacy vulnerabilities that we want our machine learning models to avoid. So the first example we'll be talking about is a generative model that's quite iconic. It's the one that's found on Google Translate. So the way this system was trained takes advantages of documents that are found in 2 different languages to learn a mapping between those 2 languages. So for example, some people once found out that for certain phrases between 2 languages, in particular when one of them isn't as widely spoken, when you sometimes inputted some phrase in one of these languages, the model actually returns some funny outputs. What's happening here is that the model ends up leaking the actual train that it's found on the training set, and it's not performing translation at all. This model's output in particular sounds kind of an apocalyptic message, which is just being inputted ... but it's actually just a passage from a biblical text, because these types of biblical documents often represent a big fraction of all those found both in English and in Yoruba. So in this case, the model just learned to memorize this example, and it's what it's returning to us. So on a similar note on this kind of vulnerability, some researchers in Berkeley experimented with inserting the following phrase, what they call a canary phrase, inside of a data set which has natural phrases. And they trained a language model on this altered data set. So the intuition that they had with this experiment was that the model should learn to generate new natural phrases instead of just memorizing individual pieces of data that are found inside of the data set. By the way, the model that they started training on was smaller in size than that of the entire data set. So they made sure that the model couldn't just memorize all the phrases found on the data set and just repeat them. But what they found is that actually when they gave the generative model as a prompt, the random number is 2812, the model just happily returned the remainder of that phrase. So this isn't much of a problem if we're just returning a random number. But one could think about how this could be a big issue if you're training large language models on vast amounts of data, and perhaps you have accidentally inside of it, I don't know, a credit card number or a social security number or any other kind of customer data or personally identified information that you just really don't want your model to accidentally leak when you're using it in production. So yeah, this is one of the possible issues that you may face. Another one, which is kind of interesting, is when you're looking at deployed face recognition APIs that are commonly found in production nowadays. Some of them, when you give them an image and you're asking them to classify it, not only return the class label, that is the person that they think it is, but they also return a floating point measure confidence that indicates how confident the model is about that prediction in particular. So in these scenarios, one can think of an attack that tries to reconstruct the faces of the persons in the training set and present this following attack as sort of an optimization problem. So for a given class label, that is for a given person's identity, try to find an input image that I've got to send the face recognition API. Try to find an input image that tries to maximize this return confidence. So in their paper, Fredrickson et al. Proposed such an algorithm that presents the problem in such a way that they use as a loss function the confidence score, and they start altering the input image that they are sending in order to maximize this expected confidence. And in this way, you can see that they were able to reconstruct the image that you can see on the left, whereas the image on the right was the one that was actually present on the training set. So yeah, these are kind of examples in which sometimes some attackers might have access to your model's internal parameters, or sometimes they just see the output of it. But in any those two scenarios, you may be leaking accidentally some information of your training set. So with those ideas in mind, let's see what differential privacy is and how it can help us guarantee that these kind of issues don't happen. Okay, so let's first say that the objective of differential privacy is to find a way that to learn about the data set as a whole, to gain intuitions about this group of people while protecting the specific information of individuals who participate in that data set. So in other words, what we're looking for is a way to quantify the impact of a person's participation in the data set. We're going to be calling this negative impact the privacy loss. That means, am I allowing my information to be used to train a machine learning model in it? Well, in order for me to make that decision, I would like to know what's the maximum possible negative impact that I could have if I participate in it. For example, if we think of the face recognition problem, the worst impact that I could have would be my face being revealed. So when we're building machine learning models, this translates into building ones that are not only useful for making predictions, but that also we can make some solid guarantees with respect of the privacy that we can guarantee to the individuals whose data was used for training them. Okay, so in order to start presenting this idea of differential privacy a bit more formally, a concept that we're going to be using a lot is one of adjacent databases. So in a nutshell, an adjacent database is the following. Let's say we have a database D. So we can say that a database D prime is adjacent to it if it has the same information as D, but it's missing that of a single individual. So for example, let's say the database D has information of John, Mary, and Mike. D prime is an adjacent database that just has information of John and Sarah, for example. So that was adjacent databases. Now let's see what we mean when we say a mechanism. A mechanism is just a way to make queries to our database. So for example, let's say we have a toy database of people's heights, and we have a mechanism M that computes the average height. So one thing that one can think about is that we could start, for example, if you think for a second that we are an attacker and we want to, for example, know the height of a particular person who is in this database. One thing that quickly comes to mind is that if I'm doing this mechanism repeatedly and suddenly a person is removed from the database, the answer of my mechanism is going to change. Because, for example, if John is removed from the database and the average height of all the people in the database now is altered, one can start looking at that difference in the mechanism's output to try to gain useful information about that person in question who has been removed. So this is the kind of information that our mechanism will be revealing when doing queries on a data set. So something that's useful to keep in mind is that in the context of machine learning models, one can think of this mechanism as doing inference on an actual trained model. So you've already built your model from your training data, then you're putting it on production, and then people are doing queries on it to obtain predictions of new unseen data. When people are making predictions, this model is inadvertently telling them the things that it has learned from the database. So this is what we say when we're talking about mechanisms in the context of machine learning. Okay, so with those two concepts in mind, let's see how we can formalize the definition of differential privacy, which will help us determine the privacy guarantees that we can actually make towards the individuals who were participating in our dataset. So let's call a randomized mechanism M to have domain D and range R. That means all the possible outputs of our mechanism fall in the range of R. And let's consider S to be a subset of all these possible outputs included in R. So for example, this subset S could be just a particular output, meaning does the mechanism respond this particular thing, or it can also be a group of possible outputs. Okay, so what are we gonna be choosing to see when we are talking about this mechanism? Well, we're applying this mechanism to different databases. In particular, we're gonna be focusing on the output of our mechanism when it's applied to two adjacent databases. We're gonna be calling these outputs O and O prime. Okay, so what kind of privacy guarantees could we give about a particular mechanism M? Well, we can say that M satisfies being epsilon differential privacy if for any two adjacent databases D and D prime, and for any subset of outputs S, it holds that the probability of the outputs of adjacent databases falling in the same range R differs no more than e to the epsilon. So this can sound like a mouthful at first, but let's try to illustrate it with some examples and try to gain some intuitions about what this inequality is telling us. So first off, you can think of epsilon as sort of a parameter that defines how much privacy loss our mechanism has. If you have a very small epsilon, it means that our mechanism is very private and it's not leaking a lot of information of any particular individual. Whereas if you have a big epsilon, it means that your mechanism is telling you useful information, but by doing so, it's also leaking more information about individuals in your dataset. Okay, so let's see what this following inequality means when we're picking epsilon 0. By the way, epsilon 0 would mean that it has perfect privacy. And that is because the inequality tells us that the outputs of adjacent databases must be exactly the same for this inequality to be true. So the only way that the numerator and the denominator are going to be less or than equal to 1 is for them to be exactly the same, because you can always flip them and never can that output be bigger than 1. So that means that we can choose any two outputs of our model or any subset S of outputs. The probability of those of the mechanism's output to fall inside the subset S needs to be always the same. So in this case, both of those outputs fall inside of S, whereas on this case, both of them fall outside of S. Since the probability is the same, the inequality holds true. Now, what happens if one would choose to use epsilon equal 5? Well, one could say that, in a sense, this allows a bit more room for a mechanism to output more different things when we remove a person from a database. So let's keep in mind that database T prime is the same as database T, but with an individual removed. So perhaps now my mechanism might leak a bit of information by allowing itself to return something different when making the same query. So for example, on this case, epsilon 5 is an arbitrary number, but it allows in the inequality for the output of our mechanisms to differ up to a certain extent. So this is, one can think of this epsilon as a way to actually quantify the amount of information that we may be leaking about any particular individual. Okay, so having this useful epsilon number in mind, one can think, okay, well, I want to like train a model on some data and actually like know how much information I may be leaking if I release this model into the public. Well, for that, we would like to think about, well, how can we sort of construct this epsilon number so that we can say, okay, here I've built this model, I'm gonna be releasing it. And when I release it, I may be really leaking this amount of information about the training set. Ideally, we want this number to be small, but I mean, we really need to find a way to sort of construct this number. And the way we do that is to first determine the privacy loss of doing a single query to our model. In this case, by the way, with query, I mean that once we deploy our model, we're gonna be doing inference on that model. And when we're doing inference, the model is returning us, in a way, information that it has learned from the data set. So each time that the model returns us new information, it's actually increasing the privacy leak that it has. So the way that we have to actually compute the total privacy leak is to determine first the privacy loss of a single query, then compound this privacy loss across all the queries that were made, and then just repeat that process as long as we are doing inference on this machine learning model.
I have a question here. You mean all
Sure.
the queries that are made throughout time, or like all the possible queries that can potentially be made? Like, can
No.
this be computed without regard to particular set of queries, like in
No.
principle?
Yeah, no, that's a good question. In fact, you're only leaking information with respect to the queries that you are doing, because each time you query your model, in a sense, it's telling you something different. So it's not all the possible queries that you could make, but the ones that you actually make. Under this scenario, if you only make a single query to your model, you're leaking less information than if you're doing 100 queries to it.
But so it can happen that, for example, there is one individual in your data set in which the model was trained, and the model kind of shifted some average towards, say, a person who is, I don't know, 3 meters tall. Then you have that in your trained model, and you do a lot of queries. And then if you actually query the height of that particular person, you might get a completely different response if the model was trained without that individual, let's say. So maybe the fact that you are not doing the query means that you're not leaking information, but there is like this one query which could cause like a big leak because you kind of know that there's a person that is very tall in this data set or something like that.
Yeah, that's actually a great question. And in fact, the way that we define differential privacy, we're talking about any two adjacent databases, D and D prime, specifically to consider those worst case scenarios of people who really deviate and really shift the output of our mechanisms in one way to another, because this epsilon needs to guarantee, in a sense, that maximum possible variation. So yeah, you really need to care about these border cases and the amounts of information that they leak, because that leak is actually gonna be the one that's the upper bound of this epsilon that we can guarantee.
There's a related question in the Q&A by Fernando Lopez, and he says, like, can you tell in advance all the possible queries? I think it's very related to what you're saying.
Can I tell in advance?
All the possible queries.
Oh, well, yeah, I mean, naturally no, because, for example, let's say that you have an inference model. I mean, you could theoretically determine all the possible, the domain of the inputs of your queries, but you really cannot in practice because the spaces, for example, of input images are so vast that it wouldn't be useful. And since this current approach currently, it impacts our privacy a lot when we are doing repeated queries. That's not an useful number. Perhaps if I go to the next slide and talk a bit about the strategy that PATE shows, this question might be easier to answer because, yeah, we don't really want to focus on all the possible queries made and all the information that could be leaked because, yeah, in that way, the privacy cost is going to grow quickly and we really don't want that to happen. So let me go a bit to the next question. And okay, so with these constraints in mind, some things that we might want to happen is, well, first of all, we would like to build our machine learning model in such a way that the final epsilon of building that model is rather small. But we would also like to have a way in which we already know the maximum privacy loss that we are going to have so that this privacy loss is fixed no matter how many times I do inference on this model. And also, I would like to have a certain way in which to start calculating this value as long as when I'm training the model on it. So yeah, what we're going to talk now is about this technique that's called PATE, which allows us, while we're training our model, to compute that maximum theoretical information loss that we could have. So that we don't have that problem of determining all the possible inputs that our model might have and all the possible information that we may accidentally leak. So let's see what PATE does in order to address these issues. Okay, let's illustrate this with an example. Let's say we have some sensible medical information and we want to build a classifier that helps us to detect illnesses while preserving the privacy of those patients. So I can think that we have all the medical history of several patients of a hospital, and we might want to build a classifier that helps us detect whether if a new patient, given their medical history, is currently ill or healthy. So first off, what we're going to do is that this data set that we have, we're going to be partitioning it on several subsets of data. And we're going to be training one model on each of these distinct subsets of the training data. And we're going to be calling all these models our teacher models. What are we going to do with these teacher models? Well, we're going to train a student model. And we're going to take advantage of the knowledge that these teachers have learned from our private data set to transfer this knowledge to our students in a controlled manner that we can, in a sense, quantify how much information the teachers are sending to our students. So if we have a way to quantify the amount of information that our teachers are passing to the students, we can actually build this upper bound of epsilon while we're doing the training on our students, because afterwards we can actually release the student model. And we know that at worst, it will have learned epsilon amount of information from our training set. So this is a way that we can actually sort of limit that sort of potential leak just by understanding the total amount of information that our model has learned from the training set. So how should we train this student model? Well, first off, we're going to be using public and labeled data to train this student model. And each of the samples of this public data is going to be passed through each of the teacher models to obtain a class predictions. So we're going to send a new sample to teacher 1, 2, and 3, and 4. And they're going to give us some predictions on whether this new patient is healthy or sick. Sometimes maybe all of them agree, and sometimes they give different answers. But we're going to be having a way to average all these answers in order to build a label to give to our students. So the idea of PATE is to building these private labels in such a way that they are not only useful so as to train the model, to train the student model, but also to sort of quantify the amount of information that these labels convey about the original training dataset. So how are we going to average all these teachers' predictions? Well, after we pass a new training sample onto the 4 of them, we just count the predictions that they have, and we add some random noise to those vote counts. In the original paper, for example, the authors proposed adding some random noise that comes from a Laplacian distribution. So, and then that most voted class with the added noise added is used as the actual training label for the student model. So after we do that for a group of public data, let's say we have already 5,000 labeled samples, we have these lab samples and their labels, and we can proceed to train the student model with it. So let's start talking about a bit about this aggregation mechanism and how it can help us not only gain some useful accuracy, but also ensure the privacy of the training data. This technique, PATE, provides actually some pleasant synergies between the privacy guarantees that it can provide and the correctness of the predicted label. For example, think of the case where the consensus between all the teachers is rather strong. In these cases, for example, if all of them predict that for a single sample, it's healthy, it's very unlikely that adding some noise to that vote count will actually change the class that received the largest number of votes. Therefore, in these cases, the accuracy of the label is rather strong. At the same time, a strong agreement between all of the teachers, offers a stronger privacy guarantees, since each member of the teacher's dataset played a smaller role in arriving to this final class table. Therefore, one could think that the removal from one of the teacher's database of a single individual is less likely to generate a variation of this average label. Because if we think for a second about the definition of differential privacy, what we're trying to do is to guarantee that the participation of a single individual in our database doesn't affect him that much. So in what way am I using the individuals in my database? Well, I'm using an individual to train one of the teacher models that is going to cast a vote on the class that it thinks that a new sample has. So if I remove one of the samples of one of the teachers and there's a high agreement, it's very unlikely that the removal is going to affect my final averaged vote. So in an intuitive sense, one can think that on these scenarios, the privacy guarantees that our mechanism gives are rather high. Also, this has another side benefit that it helps us. It helps us sort of to arrive to a more generalizable model that doesn't depend that much on memorizing particular individuals' datasets, because if one of our teacher models tends to overfit to a certain particular samples, that overfitting is not going to affect that much the average label. If, on the other side, when the teachers don't seem to agree very much on the sample of the class, their outputs counts are rather 50-50. In that cases, it is true that a single training sample coming from one of the teachers might play a bigger role in flipping that majority vote in one direction or the other. So in these scenarios, removing one of the samples of that teachers might actually reveal a bit of information when you're building this average label. So in these cases, where the privacy concern is a bit bigger, one could intuitively think that this random noise that we are adding plays a bigger role in influencing the output of our label. Therefore, it helps to protect the privacy to a bigger extent. Because in a sense, it's more likely that this random noise is going to make the average label to just be a random one, rather than revealing information from one of the teacher's training information. In fact, there's an updated version of PATE that the authors present the following year, where they have a new aggregation mechanisms that sometimes selectively discards some of the queries that we make to our teachers in order to discard these cases where the teachers don't seem to agree that much. Because in these cases is where we can actually leak the most amount of information of our training set. So these new aggregation mechanisms sometimes decides not to provide a label in cases where the agreement isn't that high. Okay, so let's keep in mind that in the aggregation mechanism is where we are building these private labels. And that's the moment where we want to sort of have sort of an accounting of how much information we are giving our student from our training set. We want to sort of start adding up bit by bit epsilon values, so that after we've labeled all the examples, we can say, okay, with all these labels, we are leaking this amount of information from our training set, which equates to this value of epsilon. So there are some techniques that we can employ when doing this aggregating mechanism to measure the privacy loss that we can have. First off, each individual predicted label that we generate incurs a small privacy loss called epsilon. All these epsilons are going to be compounded across all the queries that our student model is making to our teachers. And the way that we calculate this single individual epsilon is going to be a function of the teacher's predictions, their average prediction, and the amount of noise that we are adding. One could see on the previous examples that the amount of information that we will be leaking is not exactly the same if the agreement is very high, but it's also not going to be exactly the same if the noise that we add is very high. So all those play a role in determining how much privacy you're losing. So the techniques that we actually use in order to account for this, to compute this privacy loss, are a bit outside the scope of this talk, but in particular, there's two of them which the authors propose in these two papers, which I would highly encourage you to check if you are interested in them. One is called the moments accountant, and the other one is the RENI, differential privacy. Moments accountant can be used when we are adding Laplacian noise. It depends a bit on the kind of noise that you're adding, the mechanism that allows you to compute that epsilon. But the good news is that if you don't want to dig that deep into the maths, there's actually a very good library called PySift that's from the Open Mind organization that just allows you to have that epsilon computed. So when you're building these labels, after building them, you just give the library all the individual teacher predictions, your average predictions, and you tell them the amount of noise that you were using from the Laplacian distribution, and it's gonna just tell you the total amount of epsilon that you had while training those models. So yeah, this is another library that I would encourage you if you are trying to train machine learning models using the PATE technique, because I've personally been using it and it really helps to not to dig that much deeper into the implementations of these techniques. So yeah, that was a bit the intuition about how the PATE technique works. In particular, just to give you some sort of rough numbers, the authors proposed these experiments. They've tried training an image classifier on MNIST and SVHN. And what they've done is, for example, for MNIST, they created 100 labels to train a student model. And then they train another student model labeling 1,000 queries. Naturally, when you're using more samples, your epsilon value is going to be increasing because you're, in a sense, giving more information about that training set. But one can see that actually the accuracy of those students is not that far off from the baselines of just a traditional image classifier just trained directly on MNIST. And by the way, on these experiments, they built 250 teacher models. So the original MNIST dataset would be splitted into 150 pieces to train those teacher models, and then some other data was used to train the student on. So yeah, something else that's also useful to take into consideration is that the scalar epsilon is going to depend a lot on the problem that you have, and you might want to build up some intuitions in your particular problem, what it actually means. Having just a binary output is not the same as having a 10 class label output. So yeah, it's just a scalar and it has to be interpreted in its proper context. But it's always very useful to have this solid number that just tells you how much information you could potentially leak from your model. So I think that's going to be the last concept that I'll be introducing in this talk. So maybe I don't know if I went a bit too fast in certain areas, but if you have some questions or comments.
I think it was great, and thank you very much for the presentation. Anybody can send comments and questions to the chat and the Q&A. I have a few to start. The first one that maybe it's because of the lack of more deep statistical knowledge, but why do you use Laplacian noise versus, for example, Gaussian noise or other type of noise? Is it like some properties, special properties of the Laplace distribution?
Yeah, that's actually a great question. And in fact, the Laplacian noise was the ones that the authors introduced in their original paper in 2017. Depending on the distribution that this noise comes from, the technique that we are allowed to use in order to compute this epsilon. But they actually, on 2018, they actually tried using the Gaussian noise, and they discovered that it actually provided better results with less privacy loss. So you can always need to be very careful how you start computing this privacy loss depending on the distribution of your random noise. But yeah, if you find a way to measure this privacy loss, you can use noise coming from different distributions. I'm just seeing that there's another question that says, how do you choose epsilon? Well, epsilon, in fact, is the value of epsilon is gonna be the results of your training. It represents, in a way, how much information your students learn from your training set. So it's something that's going to be compounded across your training on the model. So it's something you mostly have to keep track of and see if the final result of your trained model, the amount of epsilon that it has, is satisfactory for your needs. And then I see another question from Eduardo. Is there a way of normalizing the value of epsilon so that one can compare with the epsilon of other experiments? Well, that's a great question. And in fact, I don't think there is one right now. It really needs to be taken into the proper context of the experiments, because yeah, as I said, having a binary classifier is not the same as having a classifier that can output, I don't know, 10 different classes, or one that just returns the identity of a face. So yeah, unfortunately, you really need to consider what's the space of the possible outputs of our model in order to understand how much information you might leak.
There's another question in the Q&A.
How do you know if epsilon is satisfactory? For example, epsilon equal 1 versus epsilon equal 10, 20. Well, that's a similar question to the previous one, in the sense that this is going to be determined a lot on your particular problem. There's really not a ground truth answer in order to answer what absolute value is acceptable or not. You really need to take into consideration the nature of the output of your mechanisms in order to determine, to have a better intuition in how much this epsilon actually means in your like practical problem.
I have another question. Maybe it's worth giving some information on, or at least some intro on federated learning, which I think is a very related topic. I don't know if you have any comments on that.
Yeah, sure. So federated learning is actually, this organization, in fact, OpenMind, provides a lot of libraries and tools that helps us build different kind of solutions that have privacy in mind. They have some solutions for federated learning, where actually the learning doesn't happen all in the same place, but actually you can have different models that train on different places. For example, if you talk about, for example, the classifier that we were mentioning that tries to predict whether a person is healthy or not, for example, think that all this medical information might be on premises inside a hospital, and they don't really want you to, they don't want to like share that information with you. They say, okay, you can train a model as long as you guarantee that it's going to be a private model. But if you want to train it, you need to train it on premises. Like the data cannot move, the model must come to us. So federated learning allows us to not only train a model, not train a model where the data is, but actually use data that comes from different sources in order to train a unique model from data that's coming from different sources. So for example, a possible approach is that sometimes what you're sending through the network are the gradient updates of your model instead of the data the model is going to be trained on. So yeah, it's not exactly the same, but it's a technique that allows you to train models when you don't actually have the data in the same place as where your model is being trained on.
Yeah, I think it's very related because of exactly that. There's like the case would be like mobile devices which learn preferences from their owner, or the predictive keyboard in your iOS or Android device. It might learn what you yourself use as the way you type, but then maybe it's sending data back to the cloud in form of a trained model that doesn't leak information, and also can do they can learn from the models trained in several different devices in a mega model that never sees the original data. So I think that these two concepts are very related, the concept of differential privacy and federated learning. There's another question in the Q&A. Can you tune the privacy laws versus accuracy laws you're comfortable with or allowed to have by compliance?
Yeah, that's actually a great question. And in fact, it's been one that I've been experimenting a lot for my particular case. And the answer is yes, you can absolutely. There's a lot of, in a way, hyperparameters that you can tune in order to find this optimal privacy and accuracy trade-off. For example, you could train more teachers if you have a lot of data, because a bigger ensemble of teachers reduces the privacy loss, that because in a way each teacher's votes is gonna comparably have a less of an impact. Also, you can increase the amount of the shape of the distribution of the from which you're sampling your noise. You can add more noise. That's gonna be increasing your privacy, but also at the same time reducing the accuracy. And so yeah, you can you can just play with different architectures, but yeah, you can always try to find that optimal balance between the amount of accuracy and the amount of epsilon that you have. In fact, the authors try with a large variety of ensembles, like a different number of ensembles, and different number of noise that they're adding to arrive to the compromise that they're most happy with.
I have another one, which is maybe like the elephant in the room in some sense. So what about compute time, efficiency?
Yeah, that's quite the elephant in the room. Yeah, the way I see it, there's a couple of limitations to this technique. One of them is, of course, compute. It's not really fun having to train 250 different models. I've done it, and when it crashes, it's not very happy. Yes, the compute costs for training the teachers are going to scale linearly. And also another thing that you might want to take into consideration is that also the size of the available data set might become a bigger issue, because you're now splitting your available labeled data set into 150 or 10 ways to teach it to train your individual models. What I've observed is that usually the accuracy of the ensemble of teachers as a whole, that means the final average label that they arrive to, is usually higher than the accuracy of individual teachers. But of course, if you have to split your data set 100 ways or 50 ways, the accuracy of the single teachers is going to be less than just training a single classifier. So yeah, those are two considerations to have in mind when you're using this technique.
And does it limit you in the sense of that you have to use particular types of models for training the teachers? Or like, can you use anything? Can you use deep learning? Can you use like XGBoost, random forest?
Yeah, that's actually a great question. And it's one of the main benefits of PATE, is that it doesn't restrict you at all in the architecture of your models. One can think that the only thing that PATE needs is a model that just returns an output. The architecture of the model itself is not going to affect the privacy loss, since that's computed based on the different votes. So yeah, you can always use a deep learning model, a random regression. The architecture itself of the models, of the teachers and the students, is irrelevant for the framework itself. In fact, you can use different architectures for the students and the teachers.
And
yeah,
go ahead.
Yeah, by the way, no, this plays nicely with the idea of federated learning, that perhaps you might want to, like, each hospital to train their own model. They can be like different models. And then you could always use like an ensemble of them. Like, you can allow to have like different teachers with different architectures to each cast a vote. So yeah, you can, in this way, it provides a lot of flexibility.
Okay. Do you have a way or some tips in order to decide what the partitioning of the data set to train the different teachers should look like? What considerations you should have when partitioning your data set?
Well, I think the considerations are similar to when you are splitting into train and validation. For example, it depends a lot on the kind of data set that you're using. Sometimes if it's just, I don't know, medical history where two samples aren't related between each other, there's not a lot of considerations to take in mind. But if you have one sample that depends from the other, for example, if you have sequential data, you need to be sure that when you split that data, there's not like correlations between data that's found and So yeah, that kind of consideration you should have.
So these splits are only a data set split. So we are not doing like the classifiers of one teacher and the other teacher, looking at different set of features in order, or that can also be done here.
I'm sorry, how?
Like, for example, I don't know, in order to predict a health condition, one model looks at whether the person, the age and whether they smoke, and the other person looks at whether they had some other health issue before. And these features are like separate from each other. So it's kind of what you're doing with the random forest in some sense.
Yeah. No, in that sense, no, you need to split the data set based on individuals, not the particular features of one of the samples. Yeah.
Okay, good. Any other questions in the chat or the Q&A? Or
yes,
no
thanks
more
for sharing.
questions, and I think unless anybody else has a comment.
Can you
we're
hear
good to
me?
go.
Yeah, I think they are making a question here. I can hear you.
Oh, okay. So yeah, thanks for sharing. That was a very interesting presentation on a subject that we we may be inadvertently falling into. So that was a very interesting consideration to have. Do you know of any environments where this is used in a production setting?
Yeah, actually, I have a useful example where they use differential privacy. Do you know, for example, and when you're searching on Google, for example, when you're searching for a particular gym or a restaurant, sometimes there's a little widget that tells you the amount of persons that are in that particular venue or by hour. So the way that Google has recollected that information of how much people are in a particular place is the following. So they gather a lot of location data from different devices. So they have some rough data points on how much people are in certain places. But the way that they aggregate this information is using differential privacy, because that's a great place where what you actually want to know is the average of how much people are at a particular place. You don't want to know if individuals are at that place or not. So the way that they compute that average is using differential privacy. It's not a PATE, it's not training machine learning differential private models, but yeah, that's an example I can think of using differential privacy.
Nice, so cool. Yeah, glad to know. Thanks.
Yeah.
All right, so any other final questions or comments? Okay, I think we're good to go. Thank you very much, Seba, for your presentation. It was great. And also for the people who sent questions, very, very good questions. And there's a lot of room for discussion here. Anybody can send further questions or comments to hello@Tryolabs.com. And this is it for today. So again, thank you everyone for joining.
Yeah, thank you very much. Goodbye.
Thank you. Bye.